This is a photo taken of the night sky. A meteor and its tail are shown entering the Earth's atmosphere. Figure 3.1 meteor showers are rare, but the probability of them occurring can be calculated. Credit. Modification of work A meteor during the peak of the 2009 Leonid meteor shower by Navicore/Wikimedia Commons, CC by 3, chapter objectives. By the end of this chapter, the student should be able to understand and use the terminology of probability, determine whether two events are mutually exclusive and whether two events are independent, calculate probabilities using the addition rules and multiplication rules. Construct and interpret contingency tables, construct and interpret Venn diagrams, construct and interpret tree diagrams. It is often necessary to guess about the outcome of an event in order to make a decision. Politicians study polls to guess their likelihood of winning an election. Teachers choose a particular course of study based on what they think students can comprehend. Doctors choose the treatments needed for various diseases based on their assessment of likely results. You may have visited a casino where people play games chosen because of the belief that the likelihood of winning is good. You may have chosen your course of study based on the probable availability of jobs. You have more than likely used probability. In fact, you probably have an intuitive sense of probability. Probability deals with the chance of an event occurring. Whenever you weigh the odds of whether or not to do your homework or to study for an exam, you are using probability. In this chapter, you will learn how to solve probability problems using a systematic approach. Collaborative exercise. Your instructor will survey your class. Count the number of students in the class today. Raise your hand if you have any change in your pocket or purse. Record the number of raised hands. Raise your hand if you rode a bus within the past month. Record the number of raised hands. Raise your hand if you answered yes to both of the first two questions. Record the number of raised hands. Use the class data as estimates of the following probabilities. P change means the probability that a randomly chosen person in your class has change in his/her pocket or purse. P bus means the probability that a randomly chosen person in your class rode a bus within the last month, and so on. Discuss your answers. Find P change, find P bus, find an bus. Find the probability that a randomly chosen student in your class has change in their pocket or purse and rode a bus within the last month. Find P change bus. Find the probability that a randomly chosen student has change given that they rode a bus within the last month. Count all the students that rode a bus. From the group of students who rode a bus, count those who have change. The probability is equal to those who have change and rode a bus divided by those who rode a bus. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. An experiment is a planned operation carried out under controlled conditions. If the result is not predetermined, then the experiment is said to be a chance experiment. Flipping one fair coin twice is an example of an experiment. A result of an experiment is called an outcome. The sample space of an experiment is the set of all possible outcomes. 3 ways to represent a sample space are to list the possible outcomes, to create a tree diagram, or to create a Venn diagram. The uppercase letter S is used to denote the sample space. For example, if you flip one fair coin, S equals H, T, where H equals heads and T equals tails are the outcomes. An event is any combination of outcomes. Uppercase letters like A and B represent events. For example, if the experiment is to flip one fair coin, event A might be getting at most one head. The probability of an event A is written P, A's. The probability of any outcome is the long-term relative frequency of that outcome. Probabilities are between 0 and 1, inclusive, that is, 0 and 1 and all numbers between these values. P A equals 0 means the event A can never happen. P A equals 1 means the event A always happens. P A equals 0.5 means the event A is equally likely to occur or not to occur. For example, if you flip one fair coin repeatedly, from 20 to 2,000 to 20,000 times, the relative frequency of heads approaches 0.5, the probability of heads. Equally likely means that each outcome of an experiment occurs with equal probability. For example, if you toss a fair, six-sided die, each face 1, 2, 3, 4, 5, or 6 is as likely to occur as any other face. If you toss a fair coin, a head H and a tail T are equally likely to occur. If you randomly guess the answer to a true-false question on an exam, you are equally likely to select a correct answer or an incorrect answer. To calculate the probability of an event A when all outcomes in the sample space are equally likely, count the number of outcomes for event A and divide by the total number of outcomes in the sample space. For example, if you toss a fair dime and a fair nickel, the sample space is HH, TH, HT, TT, where T equals tails and H equals heads. The sample space has 4 outcomes, A equals getting 1 head. There are 2 outcomes that meet this condition, HT, TH, so P, A, 24 equals 0.5. Suppose you roll one fair 6-sided die with the numbers 1, 2, 3, 4, 5, 6 on its faces. Let event E equals rolling a number that is at least 5. There are 2 outcomes, 5, 6, P, E equals 26. If you were to roll the die only a few times, you would not be surprised if your observed results did not match the probability. If you were to roll the die a very large number of times, you would expect that, overall, 26 of the rolls would result in an outcome of at least 5. You would not expect exactly 26. The long-term relative frequency of obtaining this result would approach the theoretical probability of 26 as the number of repetitions grows larger and larger. This important characteristic of probability experiments is known as the law of large numbers, which states that as the number of repetitions of an experiment is increased, the relative frequency obtained in the experiment tends to become closer and closer to the theoretical probability. Even though the outcomes do not happen according to any set pattern or order, overall, the long-term observed relative frequency will approach the theoretical probability. The word empirical is often used instead of the word observed. It is important to realize that in many situations the outcomes are not equally likely. A coin or die may be unfair or biased. 2 math professors in Europe had their statistics students test the Belgian €1 coin and discovered that in 250 trials, a head was obtained 56% of the time and a tail was obtained 44% of the time. The data seem to show that the coin is not a fair coin. More repetitions would be helpful to draw a more accurate conclusion about such bias. Some dice may be biased. Look at the dice in a game you have at home. The spots on each face are usually small holes carved out and then painted to make the spots visible. Your dice may or may not be biased. It is possible that the outcomes may be affected by the slight weight differences due to the different numbers of holes in the faces. Gambling casinos make a lot of money depending on outcomes from rolling dice, so casino dice are made differently to eliminate bias. Casino dice have flat faces. The holes are completely filled with paint having the same density as the material that the dice are made out of, so that each face is equally likely to occur. Later we will learn techniques to use to work with probabilities for events that are not equally likely. OR event: an outcome is in the event A or B if the outcome is in A or is in B or is in both A and B. The event A or B can also be written as a union B, with notation as follows. Letter 1D434, letter 1D435, for example. Let A equals 1, 2, 3, 4, 5, and B equals 4, 5, 6, 7, 8. Then letter 1D434, letter 1D435, 1, 2, 3, 4, 5, 6, 7, 8. Notice that 4 and 5 are not listed twice. And event: an outcome is in the event A and B if the outcome is in both A and B at the same time. The event A and B can also be written as an intersection B, with notation as follows. Letter 1D434, letter 1D435, for example. Let A and B be 1, 2, 3, 4, 5, and 4, 5, 6, 7, 8, respectively. Then letter 1D434, letter 1D435 equals 4, 5. The complement of event A is denoted A. Read a prime. A consists of all outcomes that are not in A. Notice that PA plus PA equals 1. For example, let S equals 1, 2, 3, 4, 5, 6, and let A equals 1, 2, 3, 4. Then A equals 5, 6. PA equals 46, PA equals 26, and PA plus PA equals 46 plus 26 equals 1. The conditional probability of a given B is written P a B. P a B is the probability that event A will occur given that the event B has already occurred. A conditional reduces the sample space. We calculate the probability of A from the reduced sample space B. The formula to calculate P a B is P a B equals where PB is greater than 0. For example, suppose we toss one fair, 6-sided die. The sample space S equals 1, 2, 3, 4, 5, 6. Let A equals face is 2 or 3 and B equals face is even 2, 4, 6. To calculate P a B, we count the number of outcomes 2 or 3 in the sample space B equals 2, 4, 6. Then we divide that by the number of outcomes B rather than S. We get the same result by using the formula. Remember that S has 6 outcomes. P a B equals letter 1 D443, letter 1 D434, and D letter 1 D435, letter 1 D443, letter 1 D435 equals the number of outcomes that are 2 or 3 and even in letter 1 D446, 6. The number of outcomes that are even in letter 1 D446, 6 equals 1636 equals 13. Understanding terminology and symbols, it is important to read each problem carefully to think about and understand what the events are. Understanding the wording is the first very important step in solving probability problems. Reread the problem several times if necessary. Clearly identify the event of interest. Determine whether there is a condition stated in the wording that would indicate that the probability is conditional. Carefully identify the condition, if any. Example 3.1 problem: the sample space S is the whole numbers starting at 1 and less than 20. S equals let event A equals the even numbers and event B equals numbers greater than 13. A equals B equals P A equals P B equals A and B equals A or B equals P A and B equals P A or B equals A equals P A equals P A plus P A equals P A B equals P B A equals. Are the probabilities equal? Try it. 3.1. The sample space S is all the ordered pairs of two whole numbers, the first from 1 to 3 and the second from 1 to 4. Example 1, 4. S equals let event A equals the sum is even and event B equals the first number is prime. A equals B equals P A equals P B equals A and B equals A or B equals P A and B equals P A or B equals B equals P B equals P A plus P A equals P A B equals P B A equals. Are the probabilities equal? Example 3.2 problem: a fair 6-sided die is rolled. Describe the sample space S, identify each of the following events with a subset of S and compute its probability. An outcome is the number of dots that show up. Event T equals the outcome is 2. Event A equals the outcome is an even number. Event B equals the outcome is less than 4. The complement of A given B given A and B A or B A or B. Event N equals the outcome is a prime number. Event I equals the outcome is 7. Solution: T equals 2, P T equals 16, A equals 2, 4, 6, P A equals 12, B equals 1, 2, 3, P B equals 12, A equals 1, 3, 5, P A equals 12, A B equals 2. P A B equals 13, B A equals 2, P B A equals 13, A and B equals 2, P A and B equals 16, A or B equals 1, 2, 3, 4, 6, P A or B equals 56, A or B equals 2. 4, 5, 6, P A or B equals 23, N equals 2, 3, 5, P N equals 12. A 6-sided die does not have 7 dots. P 7 equals 0. Try it. 3.2 A number is randomly selected between 1 to 10. Describe the sample space S, identify each of the following events with a subset of S and compute its probability. An outcome is the number selected. Event F equals the outcome is 5. Event A equals the number is more than 6. Event B equals the number is odd. The complement of B A given B given A or B A or B. Event P equals the outcome is a composite number. Event M equals the number is a multiple of 3. Example 3.3 Table 3.1 describes the distribution of a random sample S of 100 individuals, organized by sex assigned at birth and whether they are right or left-handed. Right-handed, left-handed males 43-9 females 44-4 Table 3.1 Problem. Let's denote the events M equals the subject is male, F equals the subject is female, R equals the subject is right-handed, L equals the subject is left-handed. Compute the following probabilities. The M P F P R P L P M N R P F N L P M R F P M R R P F R L P M P R M P F L P L F Solution PM equals 0.52 PF equals 0.48 PR equals 0.87 P equals 0.13 PMNR equals 0.43 PFNL equals 0.04 PMRF equals 1 PMRR equals 0.96 or L equals 0.57 PM equals 0.48 PRM equals 0.8269 rounded to 4 decimal places, PFL 0.3077 rounded to 4 decimal places, PLF equals 0.0833 try at 3.3. The table describes the distribution of a random sample S of 100 individuals, organized by gender and whether they like tea or coffee. Tea coffee men 22-26 women 16-36 Table 3.2 Let's denote the events M equals the subject is a man, W equals the subject is a woman, T equals the subject likes tea, and C equals the subject likes coffee. Compute the following probabilities. PM, PW, PT, PC, PM and T, PW and C, PM or W, PM or T, PW or C, PM, PTM, PW, CP, CW. Independent and mutually exclusive do not mean the same thing. Independent events. Two events are independent if the following are true. P A B equals P A, P B A equals P B, P A and B equals P A, P B. Two events A and B are independent events if the knowledge that one occurred does not affect the chance the other occurs. For example, the outcomes of two rolls of a fair die are independent events. The outcome of the first roll does not change the probability for the outcome of the second roll. To show two events are independent, you must show only one of the above conditions. If two events are not independent, then we say that they are dependent events. Sampling may be done with replacement or without replacement. With replacement, if each member of a population is replaced after it is picked, then that member has the possibility of being chosen more than once. When sampling is done with replacement, then events are considered to be independent, meaning the result of the first pick will not change the probabilities for the second pick. Without replacement, when sampling is done without replacement, each member of a population may be chosen only once. In this case, the probabilities for the second pick are affected by the result of the first pick. The events are considered to be dependent or not independent. If it is not known whether A and B are independent or dependent, assume they are dependent until you can show otherwise. Example 3.4 You have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Jack, Q, Queen, K, King of that suit. A sampling with replacement. Suppose you pick 3 cards with replacement. The first card you pick out of the 52 cards is the Q of spades. You put this card back, reshuffle the cards, and pick a second card from the 52 card deck. It is the 10 of clubs. You put this card back, reshuffle the cards, and pick a third card from the 52 card deck. This time, the card is the Q of spades again. Your picks are Q of spades, 10 of clubs, Q of spades. You have picked the Q of spades twice. You pick each card from the 52 card deck. Be sampling without replacement. Suppose you pick 3 cards without replacement. The first card you pick out of the 52 cards is the K of hearts. You put this card aside and pick the second card from the 51 cards remaining in the deck. It is the 3 of diamonds. You put this card aside and pick the third card from the remaining 50 cards in the deck. The third card is the J of spades. Your picks are K of hearts, 3 of diamonds, J of spades. Because you have picked the cards without replacement, you cannot pick the same card twice. Try at 3.4 You have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Jack, Q, Queen, K, King of that suit. 3 cards are picked at random. Suppose you know that the picked cards are Q of spades, K of hearts, and Q of spades. Can you decide if the sampling was with or without replacement? Suppose you know that the picked cards are Q of spades, K of hearts, and J of spades. Can you decide if the sampling was with or without replacement? Example 3.5 problem: you have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Jack, Q, Queen, and K, King of that suit. S equals spades, H equals hearts, D equals diamonds, C equals clubs. Suppose you pick 4 cards and put each card back before you pick the next card. Your cards are KH, 7D, 6D, KH. Whichever or B did you sample with replacement and which did you sample without replacement? Solution: A without replacement. B with replacement. Try it. 3.5 You have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Jack, Q, Queen, and K, King of that suit. S equals spades, H equals hearts, D equals diamonds, C equals clubs. Suppose that you sample 4 cards without replacement. Which of the following outcomes are possible? Answer the same question for sampling with replacement. QS 1D 1C QD KH 7D 6D KH QS 7D 6D. K's mutually exclusive events A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes and P, A and B equals 0. For example, suppose the sample space S equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let A equals 1, 2, 3, 4, 5, B equals 4, 5, 6, 7, 8, and C equals 7, 9. A and B equals 4, 5, P, A and B equals 210 and is not equal to 0. Therefore, A and B are not mutually exclusive. A and C do not have any numbers in common, so P, A and C equals 0. Therefore, A and C are mutually exclusive. If it is not known whether A and B are mutually exclusive, assume they are not until you can show otherwise. The following examples illustrate these definitions and terms. Example 3.6 Flip 2 fair coins. This is an experiment. The sample space is HH, HT, TH, TT, where T equals tails and H equals heads. The outcomes are HH, HT, TH, and TT. The outcomes HT and TH are different. The HT means that the first coin showed heads and the second coin showed tails. The TH means that the first coin showed tails and the second coin showed heads. Let A equals the event of getting at most 1 tail. At most 1 tail means 0 or 1 tail. Then it can be written as HH, HT, TH. The outcome HH shows 0 tails. HT and TH each show 1 tail. Let B equals the event of getting all tails. B can be written as TT. B is the complement of A, so B equals A. Also, PA plus PB equals PA. PA equals 1. The probabilities for A and for B are P. A equals 34 and PB 14. Let C equals the event of getting all heads. C equals HH. Since B equals TT, P, B, and C equals 0. B and C are mutually exclusive. B and C have no members in common because you cannot have all tails and all heads at the same time. Let D equals event of getting more than 1 tail. D equals TT, PD equals 14. Let E equals event of getting a head on the first roll. This implies you can get either a head or tail on the second roll. E equals HT, HH. P, E equals 24. Find the probability of getting at least 1, 1 or 2 tail in 2 flips. Let F equals event of getting at least 1 tail in 2 flips. F equals HT, TH, TT. P, F equals 34. Try it. 3.6 Draw 2 cards from a standard 52 card deck with replacement. Find the probability of getting at least 1 black card. Example 3.7 problem: Flip 2 fair coins. Find the probabilities of the events. Let F equals the event of getting at most 1 tail, 0 or 1 tail. Let G equals the event of getting 2 faces that are the same. Let H equals the event of getting a head on the first flip followed by a head or tail on the second flip. Are F and G mutually exclusive? Let J equals the event of getting all tails. Are J and H mutually exclusive? Solution: look at the sample space in example 3.6. 0, 0, or 1, 1 tails occur when the outcomes HH, TH, HT show up. P, F equals 34. Two faces are the same if HH or TT show up. PG equals 24. A head on the first flip followed by a head or tail on the second flip occurs when HH or HT show up. PH equals 24. F and G share HH, so P, F and G is not equal to 0, 0. F and G are not mutually exclusive. Getting all tails occurs when tails shows up on both coins, T. H's outcomes are HH and HT. J and H have nothing in common, so P, J and H equals 0. J and H are mutually exclusive. Try it. 3.7. A box has two balls, one white and one red. We select one ball, put it back in the box, and select a second ball, sampling with replacement. Find the probability of the following events. Let F equals the event of getting the white ball twice. Let G equals the event of getting two balls of different colors. Let H equals the event of getting white on the first pick. Are F and G mutually exclusive? Are G and H mutually exclusive? Example 3.8. Roll one fair, six-sided die. The sample space is 1, 2, 3, 4, 5, 6. Let event A equals a face is odd, then A equals 1, 3, 5. Let event B equals a face is even. Then B equals 2, 4, 6. Find the complement of A. The complement of A is B because A and B together make up the sample space. PA plus PB equals PA, PA equals 1. Also, PA equals 36 and PB equals 36. Let event C equals odd faces larger than 2, then C equals 3, 5. Let event D equals all even faces smaller than 5. Then D equals 2, 4. P, C, and D equals 0 because you cannot have an odd and even face at the same time. Therefore, C and D are mutually exclusive events. Let event E equals all faces less than 5. E equals 1, 2, 3, 4. Problem: are C and E mutually exclusive events? Answer yes or no. Why or why not? Solution: no. C equals 3, 5 and E equals 1, 2, 3, 4. P, C, and E equals 16. To be mutually exclusive, P, C, and E must be 0. Find P, C, A. This is a conditional probability. Recall that the event C is 3, 5 and event A is 1, 3, 5. To find PCA, find the probability of C using the sample space A. You have reduced the sample space from the original sample space, 1, 2, 3, 4, 5, 6, to 1, 3, 5. So PCA equals 23. Try it. 3.8. Let event A equals learning Spanish. Let event B equals learning German. Then A and B equals learning Spanish and German. Suppose PA equals 0.4 and PB equals 0.2. PA and B equals 0.08. Are events A and B independent? Hint: you must show one of the following. P a B equals PA, PBA equals PB, PA and B equals PA, PB. Example 3.9. Let event G equals taking a math class. Let event H equals taking a science class. Then G and H equals taking a math class and a science class. Suppose PG equals 0.6, PH equals 0.5, and PG and H equals 0.3. Are G and H independent? If G and H are independent, then you must show one of the following. PGH equals PG, PHG equals PH, PG and H equals PG, PH. Note the choice you make depends on the information you have. You could choose any of the methods here because you have the necessary information. Problem: is show that PGH equals PG. Solution: PGH equals letter 1 D443, letter 1 D43A, and letter 1 D43B, letter 1 D443, letter 1 D43B equals 0, 30. 5 equals 0.6 equals PG. Problem B. Show PG and H, PG, PH. Solution: PG, PH equals 0, 6. 0, 5 equals 0.3 equals P, G, and H. Since G and H are independent, knowing that a person is taking a science class does not change the chance that they are taking a math class. If the two events had not been independent, that is, they are dependent, then knowing that a person is taking a science class would change the chance they are taking math. For practice, show that PHG equals PH to show that G and H are independent events. Try it 3.9 in a bag. There are 6 red marbles and 4 green marbles. The red marbles are marked with the numbers 1, 2, 3, 4, 5, and 6. The green marbles are marked with the numbers 1, 2, 3, and 4. R equals a red marble, G equals a green marble, O equals an odd-numbered marble. The sample space is S equals R1, R2, R3, R4, R5, R6, G1, G2, G3, G4. S has 10 outcomes. What is P, G, and O? Example 3.1 problem. Let event C equals taking an English class. Let event D equals taking a speech class. Suppose PC equals 0.75, PD equals 0.3, PCD equals 0.75, and PC and D equals 0.225. Justify your answers to the following questions numerically. Are C and D independent? Are C and D mutually exclusive? What is PDC? Solution: yes, because PCD equals PC. No, because PC and D is not equal to 0. PDC equals letter 1 D443, letter 1 D436, and letter 1 D437, letter 1 D443, letter 1 D436 equals 0. 2,250. 75 equals 0.3. Try it. 3.1. A student goes to the library. Let events B equals the student checks out a book and D equals the student checks out a DVD. Suppose that PB equals 0.4, PD equals 0.3, and PB and D equals 0.2. Find PBD, find PDB. Are B and D independent? Are B and D mutually exclusive? Example 3.11. In a box there are 3 red cards and 5 blue cards. The red cards are marked with the numbers 1, 2, and 3, and the blue cards are marked with the numbers 1, 2, 3, 4, and 5. The cards are well shuffled. You reach into the box, you cannot see into it, and draw 1 card. Let R equals red card is drawn, B equals blue card is drawn, E equals even numbered card is drawn. The sample space S equals R1, R2, R3, B1, B2, B3, B4, B5. S has 8 outcomes. PR equals 38, PB equals 58, PR and B equals 0. You cannot draw 1 card that is both red and blue. PE equals 38. There are 3 even-numbered cards, R2, B2, and B4. PEB equals 25. There are 5 blue cards, B1, B2, B3, B4, and B5. Out of the blue cards, there are 2 even cards, B2 and B4. PBE equals 23. There are 3 even-numbered cards, R2, B2, and B4. Out of the even-numbered cards, 2 are blue. B2 and B4. The events R and B are mutually exclusive because P, R, and B equals 0. Let G equals card with a number greater than 3. G equals B4, B5, PG equals 28. Let H equals blue card numbered between 1 and 4, inclusive. H equals B1, B2, B3, B4, PGH equals 14. The only card in H that has a number greater than 3 is B4. Since 2814, PG, PGH, which means that G and H are independent. Try it 3.11. In a basketball arena, 70% of the fans are rooting for the home team. 25% of the fans are wearing blue. 20% of the fans are wearing blue and are rooting for the away team. Of the fans rooting for the away team, 67% are wearing blue. Let A be the event that a fan is rooting for the away team. Let B be the event that a fan is wearing blue. Are the events of rooting for the away team and wearing blue independent? Are they mutually exclusive? Example 3.12 problem. In a particular college class, 60% of the students are women. 50% of all students in the class have long hair. 45% of the students are women and have long hair. Of the women students, 75% have long hair. Let W be the event that a student is a woman. Let L be the event that a student has long hair. One student is picked randomly. Are the events of being a woman and having long hair independent? The following probabilities are given in this example. PW equals 0.6, PL equals 0.5 PW and L equals 0.45 PLW equals 0.75. Note, the choice you make depends on the information you have. You could use the first or last condition on the list for this example. You do not know PWL yet, so you cannot use the second condition. Solution: check whether PW and L equals PWPL. We are given that PW and L equals 0.45, but PWPL equals 0, 60, 0, 50 equals 0.3. The events of being a woman and having long hair are not independent because PW and L does not equal PWPL. Check whether PLW equals PL. We are given that PLW equals 0.75, but PL equals 0.5. They are not equal. The events of being a woman and having long hair are not independent. The events of being a woman and having long hair are not independent. Knowing that a student is a woman changes the probability that a student has long hair. Try at 3.12. Mark is deciding which route to take to work. His choices are I equals the interstate and F equals 5th Street. PI equals 0.44 and F equals 0.56. PI and F equals 0 because Mark will take only one route to work. What is the probability of PI or F? Example 3.13 problem: toss one fair coin. The coin has two sides, H and T. The outcomes are: count the outcomes. There are outcomes. Toss one fair, six-sided die. The die has 1, 2, 3, 4, 5 or 6 dots on a side. The outcomes are: count the outcomes. There are outcomes. Multiply the two numbers of outcomes. The answer is, if you flip one fair coin and follow it with the toss of one fair, six-sided die, the answer in part C is the number of outcomes size of the sample space. What are the outcomes? Hint: two of the outcomes are H1 and T6. Event A equals heads, H on the coin followed by an even number 2, 4, 6 on the die, A equals. Find PA. Event B equals heads on the coin followed by a 3 on the die, B equals. Find PB. Are A and B mutually exclusive? Hint: what is PA and B? If PA and B equals 0, then A and B are mutually exclusive. Are A and B independent? Hint: is PA and B PA/PB? If PA and B equals PA/PB, then A and B are independent. If not, then they are dependent. Solution: H and T 2, 1, 2, 3, 4, 5, 6, 6, 2, 6 equals 12 T1, T2, T3, T4, T5, T6, H1, H2, H3, H4, H5, H6. A equals H2, H4, H6. PA equals 312, B equals H3, PB equals 112. Yes, because PA and B equals 0, PA and B equals 312, 112. PA and B does not equal PA/PB, so A and B are dependent. Try at 3.13. A box has two balls, one white and one red. We select one ball, put it back in the box, and select a second ball, sampling with replacement. Let T be the event of getting the white ball twice, F the event of picking the white ball first, S the event of picking the white ball in the second drawing. Compute PT. Compute PTF. Are T and F independent? Are F and S mutually exclusive? Are F and S independent? When calculating probability, there are two rules to consider when determining if two events are independent or dependent, and if they are mutually exclusive or not. The multiplication rule: if A and B are two events defined on a sample space, then PA and B, PB, P, a B. This rule may also be written as P a B equals letter 1 D443, letter 1 D434, and letter 1 D435, letter 1 D443, letter 1 D435. The probability of a given B equals the probability of A and B divided by the probability of B. If A and B are independent, then P a B equals P A. Then PA and B equals P a B. PB becomes PA and B equals PA PB. The addition rule: if A and B are defined on a sample space, then PA or B equals PA plus PB, PA and B. If A and B are mutually exclusive, then PA and B equals 0. Then PA or B equals PA plus PB, PA and B becomes PA or B equals PA plus PB. Example 3.14. Klaus is trying to choose where to go on vacation. His two choices are A equals New Zealand and B equals Alaska. Klaus can only afford one vacation. The probability that he chooses A is P. A equals 0.6, and the probability that he chooses B is P. B equals 0.35. P, A, and B equals 0 because Klaus can only afford to take one vacation. Therefore, the probability that he chooses either New Zealand or Alaska is P, A, or B equals P, A plus P, B equals 0.6 plus 0.35 equals 0.95. Note that the probability that he does not choose to go anywhere on vacation must be 0.05. Try it. 3.14. Anna has to buy a new car. She has two choices, car A and car B. Anna can afford only one car. The probability that Anna will buy car A is letter 1d443, letter 1d434 equals 0.25, and the probability that Anna will buy car B is letter 1d443, letter 1d435 equals 0.65. Find letter 1d443, letter 1d434 A and D B, letter 1d443, letter 1d434 ORB. Example 3.15. Carlos plays college soccer. He makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in a row in the next game. A equals the event Carlos is successful on his first attempt. P, A equals 0.65. B equals the event Carlos is successful on his second attempt. P, B equals 0.65. Carlos tends to shoot in streaks. The probability that he makes the second goal given that he made the first goal is 0.9. Problem A. What is the probability that he makes both goals? What is the probability that Carlos makes either the first goal or the second goal? C. Are A and B independent? D. Are A and B mutually exclusive? Solution of the problem is asking you to find P, A, and B equals P, B, and A. Since P, B, A equals 0.9, P, B, and A equals P, B, A, P, A equals 0.90, 0.65 equals 0.585. Carlos makes the first and second goals with probability 0.585. B. The problem is asking you to find P, A, or B. P, A, or B equals P, A plus P, B, P, A, and B equals 0.65 plus 0.65, 0.585 equals 0.715. Carlos makes either the first goal or the second goal with probability 0.715. See, no, they are not because P, B, and A equals 0.585. P, B, P, A equals 0.65, 0.65 equals 0.4230, 423 not equal to 0.585 equals P, B, and A, so P, B, and A is not equal to P, B, P, A. D. No, they are not because P, A, and B equals 0.585. To be mutually exclusive, P, A, and B must equal 0. Try it. 3.15. Helen plays basketball. For free throws, she makes the shot 75% of the time. Helen must now attempt 2 free throws. C equals the event that Helen makes the first shot. P, C equals 0.75. D equals the event Helen makes the second shot. P, D equals 0.75. The probability that Helen makes the second free throw given that she made the first is 0.85. What is the probability that Helen makes both free throws? Example 3.16. A community swim team has 150 members. 75 of the members are advanced swimmers. 47 of the members are intermediate swimmers. The remainder are novice swimmers. 40 of the advanced swimmers practice 4 times a week. 30 of the intermediate swimmers practice 4 times a week. 10 of the novice swimmers practice 4 times a week. Suppose one member of the swim team is chosen randomly. Problem A. What is the probability that the member is a novice swimmer? What is the probability that the member practices 4 times a week? C. What is the probability that the member is an advanced swimmer and practices 4 times a week? D. What is the probability that a member is an advanced swimmer and an intermediate swimmer? Are being an advanced swimmer and an intermediate swimmer mutually exclusive? Why or why not? E. Are being a novice swimmer and practicing 4 times a week independent events? Why or why not? Solution A. 28,150 B, 80,150 C, 40,150 D. P advanced and intermediate equals 0, so these are mutually exclusive events. A swimmer cannot be an advanced swimmer and an intermediate swimmer at the same time. No, these are not independent events. N practices 4 times per week equals 0.0667 P novice. P practices 4 times per week equals 0.0996 0.0667 not equal to 0.0996 try at 3.16. A school has 200 seniors of whom 140 will be going to college next year. 40 will be going directly to work. The remainder are taking a gap year. 50 of the seniors going to college play sports. 30 of the seniors going directly to work play sports. 5 of the seniors taking a gap year play sports. What is the probability that a senior is taking a gap year? Example 3.17 Felicity attends Modesto JC in Modesto, CA. The probability that Felicity enrolls in a math class is 0.2, and the probability that she enrolls in a speech class is 0.65. The probability that she enrolls in a math class given that she enrolls in speech class is 0.25. Let M equals math class, S equals speech class, MS equals math given speech problem. What is the probability that Felicity enrolls in math and speech? Find P, M, and S equals P, M, S, P, S. What is the probability that Felicity enrolls in math or speech classes? Find P, M, or S equals P, M plus P, S, P, M, and S. Are M and S independent? Is P, M, S equals P, M? Are M and S mutually exclusive? Is P, M, and S equals 0? Solution: a 0.1625, B 0.6875, C no, D no. Try at 3.17. A student goes to the library. Let events B equals the student checks out a book and D equals the student checks out a DVD. Suppose that P of B equals 0.4, PD equals 0.3, and PDB equals 0.5. Find P, B, and D. Find P, B, or D. Example 3.18 Studies show that about 1 woman in 7, approximately 14.3%, who live to be 90 will develop breast cancer. Suppose that of those women who develop breast cancer, a test is negative 2% of the time. Also suppose that in the general population of women, the test for breast cancer is negative about 85% of the time. Let B equals woman develops breast cancer and let N equals tests negative. Suppose 1 woman is selected at random. Problem A. What is the probability that the woman develops breast cancer? What is the probability that woman tests negative? Given that the woman has breast cancer, what is the probability that she tests negative? C. What is the probability that the woman has breast cancer and tests negative? D. What is the probability that the woman has breast cancer or tests negative? E. Are having breast cancer and testing negative independent events? F. Are having breast cancer and testing negative mutually exclusive? Solution: A. PB equals 0.143, PN equals 0.85B, PNB equals 0.02C, PB and N, PB, PNB equals 0.143, 0.02 equals 0.0029D. PB or N equals PB plus PN, PB and N equals 0.143 plus 0.85, 0.0029 equals 0.9901E. No. Pn equals 0.85, Pnb equals 0.02, so Pnb does not equal Pn. F number Pb and N equals 0.0029. For B and N to be mutually exclusive, P, B, and N must be 0. Try at 3.18. A school has 200 seniors of whom 140 will be going to college next year. 40 will be going directly to work. The remainder are taking a gap year. 50 of the seniors going to college play sports. 30 of the seniors going directly to work play sports. 5 of the seniors taking a gap year play sports. What is the probability that a senior is going to college and plays sports? Example 3.19 problem. Refer to the information in example 3.18. P equals tests positive. Given that a woman develops breast cancer, what is the probability that she tests positive? Find P, PB equals 1 P, NB. What is the probability that a woman develops breast cancer and tests positive? Find P, B, and P equals P, PB, PB. What is the probability that a woman does not develop breast cancer? Find PB equals 1 PB. What is the probability that a woman tests positive for breast cancer? Find PP equals 1 PN. Solution is 0.98, B 0.1401, C 0.857, D 0.15. Try it. 3.19. A student goes to the library. Let events B equals the student checks out a book and D equals the student checks out a DVD. Suppose that PB equals 0.4, PD equals 0.3, and PDB equals 0.5. Find PBs, find PD and B, find PBD, find PD and B, find PDB. A contingency table provides a way of portraying data that can facilitate calculating probabilities. The table helps in determining conditional probabilities quite easily. The table displays sample values in relation to two different variables that may be dependent or contingent on one another. Later on, we will use contingency tables again, but in another manner. Example 3.2 problem. Suppose a study of speeding violations and drivers who use cell phones produced the following fictional data. Speeding violation in the last year, no speeding violation in the last year total. Uses cell phone while driving 25, 280, 305. Does not use cell phone while driving 45, 405, 450 total, 7680, 5755. Table 3.3. The total number of people in the sample is 755. The row totals are 305 and 450. The column totals are 70 and 685. Notice that 305 plus 450 equals 755 and 70 plus 685 equals 755. Calculate the following probabilities using the table. A find P driver is a cell phone user. B find had no violation in the last year. C find P driver had no violation in the last year and was a cell phone user. D find P driver is a cell phone user or driver had no violation in the last year. E find P driver is a cell phone user given driver had a violation in the last year. F find P driver had no violation last year given driver was not a cell phone user. Solution: a number of cell phone users. Total number in study equals 305,755. B. Number that had no violation. Total number in study equals 685,755. C. 280,755. D. 305,755 plus 685,755 minus 280,755 equals 710,755. E. 2570. The sample space is reduced to the number of drivers who had a violation. F. 405,450. The sample space is reduced to the number of drivers who were not cell phone users. Try it. 3.2 Table 3.4 shows the number of athletes who stretch before exercising and how many had injuries within the past year. Injury in last year, no injury in last year. Total stretches 55, 295, 350. Does not stretch 230, 1, 219, 450. Total 280, 6, 514, 800. Table 3.4. What is stretches before exercising? What is stretches before exercising? No injury in the last year. Example 3.21 Table 3.5 shows a random sample of 100 hikers and the areas of hiking they prefer. Sex the coastline near lakes and streams on mountain peaks. Total women 18, 16, 45 men 14, 55 total 41. Table 3.5 Hiking area preference problem. Complete the table. Solution: a sex the coastline near lakes and streams on mountain peaks. Total women 18, 16, 11, 45 men 16, 25, 14, 55 total 34, 41, 25, 100. Table 3.6 Hiking area preference problem. B. Are the events being a woman and preferring the coastline independent events? Let F equals being a woman and let C equals preferring the coastline. Find P, F, and C. Find P, F, P, C. Are these two numbers the same? If they are, then F and C are independent. If they are not, then F and C are not independent. Solution B. PF and C equals 18,100 equals 0.18 PF, PC equals 45,100, 34,100 equals 0, 45, 0, 34 equals 0.153 PF and C not equal to PF, PC, so the events F and C are not independent. Problem C. Find the probability that a person is a man given that the person prefers hiking near lakes and streams. Let M equals being a man and let L equals prefers hiking near lakes and streams. What word tells you this is a conditional? Fill in the blanks and calculate the probability. P equals, is the sample space for this problem all 100 hikers? If not, what is it? Solution C. The word given tells you that this is a conditional. PML equals 2,541. No, the sample space for this problem is the 41 hikers who prefer lakes and streams. Problem D. Find the probability that a person is a woman or prefers hiking on mountain peaks. Let F equals being a woman and let P equals prefers mountain peaks. Find P, F, find P, P, find P, F and P. Find P, F, or P. Solution D. PF equals 45,100 P. P equals 25,100 PF and P equals 11,100 PF or P equals 45,100 plus 25,100, 11,100, 59,100. Try. At 3.21 table 3.7 shows a random sample of 200 cyclists and the routes they prefer. Let O equals older and H equals hilly path. Age group lake path, hilly path, wooded path, total younger 45, 38, 27, 110, older 26, 52, 1290, total 71, 90, 39, 200. Table 3.7 out of the older group. What is the probability that the cyclist prefers a hilly path? Are the events being older and preferring the hilly path independent events? Example 3.22 Muddy Mouse lives in a cage with 3 doors. If Muddy goes out the first door, the probability that he gets caught by Alyssa the cat is 15 and the probability he is not caught is 45. If he goes out the second door, the probability he gets caught by Alyssa is 14 and the probability he is not caught is 34. The probability that Alyssa catches Muddy coming out of the third door is 12 and the probability she does not catch Muddy is 12. It is equally likely that Muddy will choose any of the 3 doors, so the probability of choosing each door is 13. Caught or not door 1 door 2 door 3 total caught 115 112 16 not caught 415 312 16 total 1 table 3.8 door choice the first entry 115 equals 15. 13 is P door 1 and caught the entry 415 equals 45. 13 is 1 and not caught verify. The remaining entries. Problem A. Complete the probability contingency table. Calculate the entries for the totals. Verify that the lower right corner entry is 1. What is the probability that Alyssa does not catch Muddy? C. What is the probability that Muddy chooses door 1 or door 2 given that Muddy is caught by Alyssa? Solution. Caught or not door 1 door 2 door 3 total caught 115 112 16 1900 16 not caught 415 312 16 4160 total 515 412 26 1 table 3.9 door choice B. 4160C, 919. Try at 3.22 Anna has to buy a new car. She has 2 choices, car A and car B. Anna can afford only 1 car. The probability that Anna will buy car A is letter 1 D443, letter 1 D434, equals 0.25, and the probability that Anna will buy car B is letter 1 D443, letter 1 D435, equals 0.65. Find letter 1 D443, letter 1 D434, A and D B, letter 1 D443, letter 1 D434, ORB. Example 3.23 Table 3.1 contains the number of crimes per 100. 0 inhabitants in the United States over the span of several years. Year: robbery, burglary, vandalism, vehicle total 145, 732, 129, 7314, 72 133, 1717, 729, 1259, 23 119, 3700 127, 7239, 14 113, 7702, 226, 8 229, 6 total table. 3.1 United States Crime Index rates per 100. 0 inhabitants problem total each column and each row. Total data equals 4520.7 Find P, year 2 and robbery. Find P year 3 and burglary. Find P year 3 OR burglary. Find P year 4 vandalism. Find P vehicle year 1. Solution A. 0.0294, B 0.1551, C 0.7165, D 0.2365, E 0.2575. Try it. 3.23 Table 3.11 relates the weights and heights of a group of individuals participating in an observational study. Weight/height: tall, medium, short. Totals: overweight 18-28, 14. Typical weight range 20-51-28, underweight 12-25, 9. Totals. Table 3.11. Find the total for each row and column. Find the probability that a randomly chosen individual from this group is tall. Find the probability that a randomly chosen individual from this group is overweight and tall. Find the probability that a randomly chosen individual from this group is tall given that the individual is overweight. Find the probability that a randomly chosen individual from this group is overweight given that the individual is tall. Find the probability a randomly chosen individual from this group is tall and underweight. Are the events overweight and tall independent? Sometimes, when the probability problems are complex, it can be helpful to graph the situation. Tree diagrams and Venn diagrams are two tools that can be used to visualize and solve conditional probabilities. Tree diagrams. A tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and solve. The following example illustrates how to use a tree diagram. Example 3.24. In an urn, there are 11 balls. 3 balls are red R and 8 balls are blue B. Draw 2 balls one at a time with replacement. With replacement means that you put the first ball back in the urn before you select the second ball. The tree diagram using frequencies that show all the possible outcomes follows. This is a tree diagram with branches showing frequencies of each draw. The first branch shows 2 lines, 8B and 3R. The second branch has a set of 2 lines, 8B and 3R for each line of the first branch. Multiply along each line to find 64BB, 24BR, 24RB, and 9RR. Figure 3.2 total equals 64 plus 24 plus 24 plus 9 equals 121. The first set of branches represents the first draw. The second set of branches represents the second draw. Each of the outcomes is distinct. In fact, we can list each red ball as R1, R2, and R3, and each blue ball as B1, B2, B3, B4, B5, B6, B7, and B8. Then the 9RR outcomes can be written as R1, 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 R2, R1, R3, R2, R1, R2, 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 R3, R3, R1, R3, R2. R3, R3. The other outcomes are similar. There are a total of 11 balls in the urn. Draw 2 balls one at a time with replacement. There are 11 equals 121 outcomes, the size of the sample space. Problem: list the 24 BR outcomes, B1 R1, B1 R2, B1 R3. Using the tree diagram, calculate PRR. C. Using the tree diagram, calculate P, RB, or BR. D. Using the tree diagram, calculate P, R on first draw and B on second draw. E. Using the tree diagram, calculate P, R on second draw given B on first draw. F. Using the tree diagram, calculate P, BB. G. Using the tree diagram, calculate P, B on the second draw given R on the first draw. Solution: a B1 R1, B1 R2, B1 R3, B2 R1, B2 R2, B2 R3, B3 R1, B3 R2, B3 R3, B4 R1, B4 R2. B4 R3, B5 R1, B5 R2, B5 R3, B6 R1, B6 R2, B6 R3, B7 R1, B7 R2, B7 R3, B8 R1. B8 R2, B8 R3B. PRR equals 311, 311 equals 9121 C. PRB or BR equals 311, 811 plus 811, 311 equals 48,121 D. P R on first draw and B on second draw equals P RB equals 311, 811 equals 24,121 E. P R on second draw given B on first draw equals P R on second B on first equals 2,488 equals 311. This problem is a conditional one. The sample space has been reduced to those outcomes that already have a blue on the first draw. There are 24 plus 64 equals 88 possible outcomes, 24 BR and 64 BB. 24 of the 88 possible outcomes are BR. 2488 equals 311. FP BB equals 64,121 G. P B on second draw R on first draw equals 811. There are 9 plus 24 outcomes that have R on the first draw, 9 RR and 24 RB. The sample space is then 9 plus 24 equals 33. 24 of the 33 outcomes have B on the second draw. The probability is then 2,433. Try at 3.24 in a standard deck. There are 52 cards. 12 cards are face cards, event F, and 40 cards are not face cards, event N. Draw 2 cards one at a time with replacement. All possible outcomes are shown in the tree diagram as frequencies. Using the tree diagram, calculate P, FF. This is a tree diagram with branches showing frequencies of each draw. The first branch shows 2 lines. 12F and 40N. The second branch has a set of 2 lines, 12F and 40N, for each line of the first branch. Multiply along each line to find 144 FF, 480 FN, 480 NF, and 1600 NN. Figure 3.3 example 3.25. An urn has 3 red marbles and 8 blue marbles in it. Draw 2 marbles one at a time, this time without replacement, from the urn. Without replacement means that you do not put the first ball back before you select the second marble. Following is a tree diagram for this situation. The branches are labeled with probabilities instead of frequencies. The numbers at the ends of the branches are calculated by multiplying the numbers on the 2 corresponding branches. For example, 311, 210 equals 6,110. This is a tree diagram with branches showing probabilities of each draw. The first branch shows 2 lines, B811 and R311. The second branch has a set of 2 lines for each first branch line. Below B811 are B710 and R310. Below R311 are B810 and R210. Multiply along each line to find BB56110, BR24110, RB24110, and RR6110. Figure 3.4 total equals 56 plus 24 plus 24 plus 6,110 equals 110,110 equals. One note: if you draw a red on the first draw from the 3 red possibilities, there are 2 red marbles left to draw on the second draw. You do not put back or replace the first marble after you have drawn it. You draw without replacement so that on the second draw there are 10 marbles left in the urn. Calculate the following probabilities using the tree diagram. Problem: a PRR equals B. Fill in the blanks. PRB or BR equals 311, 810 plus equals 48,110 C. PR on second, B on first equals D. Fill in the blanks. PR on first and B on second equals P. RB equals 24,110 E. Find PBB. F. Find PB on second, R on first. Solution A. PRR equals 311, 210 equals 6,110 B. PRB or BR equals 311, 810 plus 811, 310 equals 48,110 C. PR on second, B on first equals 310 D. PR on first and B on second equals PRB equals 311, 810 equals 24,110 E. PBB equals 811, 710 F. Using the tree diagram, PB on second, R on first, PRB equals 810. If we are using probabilities, we can label the tree in the following general way. This is a tree diagram for a 2-step experiment. The first branch shows first outcome, PB and PR. The second branch has a set of two lines for each line of the first branch. The probability of B given B equals P, BB. The probability of R given B equals P, RB. The probability of B given R equals P, BR. And the probability of R given R equals P, RR. PRR here means PR on second, R on first. PBR here means PB on second, R on first. PRB here means PR on second, B on first. PBB here means PB on second, B on first. Try it 3.25 in a standard deck. There are 52 cards. 12 cards are face cards F and 40 cards are not face cards N. Draw 2 cards one at a time without replacement. The tree diagram is labeled with all possible probabilities. This is a tree diagram with branches showing frequencies of each draw. The first branch shows two lines, F1252 and N4052. The second branch has a set of two lines, F1152 and N4051, for each line of the first branch. Multiply along each line to find FF1212652, FN482652, NF482652, and NN1562652. Figure 3.5 Find P, FN, or NF. Find P, NF. Find P at most one face card. Hint, at most one face card means 0 or one face card. Find P at least one face card. Hint. At least one face card means 1 or 2 face cards. Example 3.26, a litter of kittens available for adoption at the Humane Society has 4 tabby kittens and 5 black kittens. A family comes in and randomly selects 2 kittens without replacement for adoption. This is a tree diagram with branches showing probabilities of kitten choices. The first branch shows 2 lines, T49 and B59. The second branch has a set of 2 lines for each first branch line. Below T49 are T38 and B58. Below B59 are T48 and B48. Multiply along each line to find probabilities of possible combinations. Problem: what is the probability that both kittens are tabby? 12B, 49C, 4938D, 4959. What is the probability that one kitten of each coloring is selected? A 4959B. C, 4959 plus 59, 49D. 4958 plus 59, 48. What is the probability that a tabby is chosen as the second kitten when a black kitten was chosen as the first? What is the probability of choosing 2 kittens of the same color? Solution: a C, B, D, C48, D 3272. Try it 3.26. Suppose there are 4 red balls and 3 yellow balls in a box. 2 balls are drawn from the box without replacement. What is the probability that 1 ball of each coloring is selected? Venn diagram. A Venn diagram is a picture that represents the outcomes of an experiment. It generally consists of a box that represents the sample space S together with circles or ovals. The circles or ovals represent events. Example 3.27. Suppose an experiment has the outcomes 1, 2, 3, 12 where each outcome has an equal chance of occurring. Let event A equals 1, 2, 3, 4, 5, 6 and event B equals 6, 7, 8, 9. Then A and B equals 6 and ORB equals 1, 2, 3, 4, 5, 6, 7, 8, 9. The Venn diagram is as follows. A Venn diagram. An oval representing set A contains the values 1, 2, 3, 4, 5, and 6. An oval representing set B also contains the 6 along with 7, 8, and 9. The values 10, 11, and 12 are present but not contained in either set. Figure 3.6. Try it 3.27. Suppose an experiment has outcomes black, white, red, orange, yellow, green, blue, and purple, where each outcome has an equal chance of occurring. Let event C equals green, blue, purple, and event P equals red, yellow, blue. Then C and P equals blue and CORP equals green, blue, purple, red, yellow. Draw a Venn diagram representing this situation. Example 3.28. Flip 2 fair coins. Let A equals tails on the first coin. Let B equals tails on the second coin. Then A equals TT, and B equals TT. Therefore, A and B equals TT. ORB equals TH, TT. The sample space when you flip two fair coins is x equals HH, HT, TH, TT. The outcome HH is in neither A nor B. The Venn diagram is as follows. This is a Venn diagram. An oval representing set A contains tails plus heads and tails plus tails. An oval representing set B also contains tails plus tails, along with heads plus tails. The universe S contains heads plus heads, but this value is not contained in either set A or B. Figure 3.7. Try it. 3.28. Roll a fair, six-sided die. Let A equals a prime number of dots is rolled. Let B equals an odd number of dots is rolled. Then A equals 2, 3, 5, and B equals 1, 3, 5. Therefore, A and B equals 3, 5, or B equals 1, 2, 3, 5. The sample space for rolling a fair die is S equals 1, 2, 3, 4, 5, 6. Draw a Venn diagram representing this situation. Example 3.29. 40% of the students at a local college belong to a club and 50% work part-time. 5% of the students work part-time and belong to a club. Draw a Venn diagram showing the relationships. Let C equals student belongs to a club and PT equals student works part-time. This is a Venn diagram with one set containing students in clubs and another set containing students working part-time. Both sets share students who are members of clubs and also work part-time. The universe is labeled S. Figure 3.8. If a student is selected at random, find the probability that the student belongs to a club. PC equals 0.4. The probability that the student works part-time. PT equals 0.5. The probability that the student belongs to a club and works part-time. PC and PT equals 0.05. The probability that the student belongs to a club given that the student works part-time. Letter 1 D443. Letter 1 D436, letter 1 D443, letter 1 D447, equals letter 1 D443, letter 1 D436, and letter 1 D443, letter 1 D447, letter 1 D443, letter 1 D443, letter 1 D447, equals 005050 equals 0.1, the probability that the student belongs to a club or works part-time. PC or PT equals PC plus PT, PC and PT equals 0.4 plus 0.5, 0.05 equals 0.85. Try it. 3.29. 50% of the workers at a factory work a second job. 25% have a spouse who also works. 5% work a second job and have a spouse who also works. Draw a Venn diagram showing the relationships. Let W equals works a second job and S equals spouse also works. Example 3.3. Problem: a person with type O blood and a negative Rh factor, Rh, can donate blood to any person with any blood type. 4% of African Americans have type O blood and a negative Rh factor. 5–10% of African Americans have the Rh factor, and 51% have type O blood. This is an empty Venn diagram showing two overlapping circles. The left circle is labeled O and the right circle is labeled Rh. Figure 3.9. The O circle represents the African Americans with type O blood. The Rh oval represents the African Americans with the Rh factor. We will take the average of 5% and 10% and use 7.5% as the percent of African Americans who have the Rh factor. Let O equals African American with type O blood and R equals African American with Rh factor. P, O, P, R equals P, O and R equals P, O or R equals. In the Venn diagram, describe the overlapping area using a complete sentence. In the Venn diagram, describe the area in the rectangle but outside both the circle and the oval using a complete sentence. Solution: A 0.51, B 0.075, C 0.04, D 0.545. E. The area represents the African Americans that have type O blood and the Rh factor. F. The area represents the African Americans that have neither type O blood nor the Rh factor. Try it. 3.3. In a bookstore, the probability that the customer buys a novel is 0.6, and the probability that the customer buys a nonfiction book is 0.4. Suppose that the probability that the customer buys both is 0.2. Draw a Venn diagram representing the situation. Find the probability that the customer buys either a novel or a nonfiction book. In the Venn diagram, describe the overlapping area using a complete sentence. Suppose that some customers buy only compact discs. Draw an oval in your Venn diagram representing this event. Stats Lab Probability Topics Class Time. Names, Student Learning Outcomes. The student will use theoretical and empirical methods to estimate probabilities. The student will appraise the differences between the two estimates. The student will demonstrate an understanding of long-term relative frequencies. Do the experiment count out 40 mixed color M and MS registered, which is approximately one small bag's worth. Record the number of each color in Table 3.12. Use the information from this table to complete Table 3.13. Next, put the M and MS in a cup. The experiment is to pick two M and MS one at a time. Do not look at them as you pick them. The first time through, replace the first M and M before picking the second one. Record the results in the with replacement column of Table 3.14. Do this 12 times. The second time through, after picking the first M and M, do not replace it before picking the second one. Then, pick the second one. Record the results in the without replacement column section of Table 3.13. After you record the pick, put both M and MS back. Do this a total of 12 times also. Use the data from Table 3.14 to calculate the empirical probabilities shown in Table 3.15. Leave your answers in unreduced fractional form. Do not multiply out any fractions. Color quantity yellow, Y green, G blue, BL brown, B orange, O red. R Table 3.12 population with replacement without replacement reds P R1 B2 or B1 R2 P R1 and G2 P G2 R1 P no yellows P doubles P no doubles. Table 3.13 theoretical probabilities. Note G2 equals green on second pick. R1 equals red on first pick, B1 equals brown on first pick, B2 equals brown on second pick. Doubles equals both picks are the same color.
With replacement without replacement.
Table 3.14 empirical results with replacement without replacement reds P R1 B2 or B1 R2 P R1 and G2 P G2 R1 P no yellows P doubles P no doubles. Table 3.15 empirical probabilities. Discussion questions. Why are the with replacement and without replacement probabilities different? Convert P no yellows to decimal format for both theoretical with replacement and for empirical with replacement. Round to 4 decimal places. Theoretical with replacement, P no yellows equals empirical with replacement. P no yellows equals are the decimal values close? Did you expect them to be closer together or farther apart? Why? If you increase the number of times you picked 2M and MS to 240 times, why would empirical probability values change? Would this change, see Part 3, cause the empirical probabilities and theoretical probabilities to be closer together or farther apart? How do you know? Explain the differences in what P G1 and R2 and P R1 G2 represent. Hint: think about the sample space for each probability.